Welcome to the deep dive. Today, we are really getting into the weeds on Moonshot AI's Kimi K2 models. We're looking at the tech papers, the key Hacker News discussions, because there's this palpable excitement building. Engineers are genuinely calling it an AI inflection point.
Yeah, it feels different this time. Pragmatic excitement, you could say.
Exactly. So our mission today is simple. Forget the flashy 1 trillion parameter headline for a second. We want to understand the real tech shifts, the economic friction, and maybe the strategic plays that Kimi K2 actually unlocks, all synthesized from those papers in that HN thread, 4583607.
Right. And to make sense of it all, we're kind of structuring this around three main things. First, the tech itself, how they even build this. Second, the bigger picture, China's open source strategy here. And third, how this shakes up the market.
Sounds good. Where do we start?
Well, before anything else, the single most critical detail, I really want to stress this up front. The story here is absolutely not the model's size. If you remember one thing, remember this. It's all about its efficiency, how it works, how much it costs to run.
Okay, efficiency. Let's unpack that because, 1.04 trillion parameters. That sounds like brute force. It dominates the headlines. So if that number is, a bit of a mirage, what's the technical reality developers should care about?
The reality is the architecture. It's a mixture of experts model and MoE,
Yeah.
but it's what they call ultra-sparse.
Ultra-sparse, meaning?
Meaning that 1.04 trillion, that's like the total library size. But when you actually use the model for any given piece of text, any token, it only activates about 32 billion parameters.
Wow, okay, 32 billion active out of over a trillion. That's a huge difference.
Massive. Think of it like this huge library, a trillion books, right?
Mm-hmm.
But for any question you ask, it only needs to pull like 32 very specific books off the shelf. They have 384 total experts, these specialized blocks, but a routing mechanism picks just 8 of them, plus one shared one for each step.
And that difference, 1T versus 32B active, that's the core engineering trick. That's what keeps it usable cost-wise.
That's the genius right there. It makes running something this enormous actually feasible.
But hang on, MoE models, especially at this scale, they're notoriously hard to train, aren't they? Stability's a nightmare. Training something that sparse, that big, on 15.5 trillion tokens, how did they even manage that? That's a known R&D hurdle.
Yeah, it's a huge hurdle.
Ah.
And they basically needed breakthroughs across the whole stack, full stack mastery, really.
Mm-hmm.
For stability, they developed their own muon optimizer. They claim it significantly outperforms standard stuff like AtomW.
Okay.
And crucially, they tackled this problem called logit explosion, where the training numbers just go wild and collapse. They use a stability technique they developed called muon clip, or QK clip specifically.
U1 clip. Okay, so they solved the training puzzle. But efficiency isn't just training, it's running the thing, inference. With these giant MoE models, isn't the memory footprint, the VRAM needed, often the real killer? Especially for long context. How'd they handle that?
Ah, yes. The VRAM constraint. That's where their big inference innovation comes in. Multi-head latent attention, or MLA. See, normal attention mechanisms store this memory history, the key value cache, the KV cache, and that cache just grows and grows with longer inputs. It eats your VRAM.
Right. I know the problem.
MLA tackles this using something called low-rank key value joint compression.
Okay. Low-rank key value joint compression. Break that down for us. What's it mean in practice?
Basically, instead of storing every single piece of the conversation history separately in that KV cache, they compress the important bits of that memory stream into a much smaller summary, a latent vector. Think of it like making a highlight reel instead of keeping the whole raw footage.
Got it. So smaller memory footprint.
Drastically smaller. Less VRAM needed, less computation. It makes running this beast affordable in production. That's key.
And they didn't stop there with efficiency, right? There was that other variant, the Kimi K2 thinking one.
Exactly. They've released that with native INT4 quantization.
Meaning it was trained for that lower precision format.
Precisely. Not just quantized after the fact. They claim lossless reductions in speed and memory use because of it. And you see it in the download size. The regular K2 is like 1.03 terabytes. The INT4 thinking variant, just 594 gigabytes. Much more manageable.
Incredible engineering.
Yeah.
Which brings us nicely to the market side. You mentioned variants. Kimi K2 Instruct and Kimi K2 Thinking. We need to distinguish those.
Yeah, it's a very clear split strategically. The Instruct model is your workhorse. General purpose, good at following standard instructions. It's state-of-the-art on benchmarks like MMLU, your reflex model.
Standard stuff, but top tier.
Right. But the thinking model, that's the specialist. They explicitly built it as a thinking agent for what they call interleaved reasoning.
Agentic capability. That's the buzzword here. What does that mean in Kimi's case?
It means it can execute a long sequence of actions using tools
Yeah.
like calculators or simulators without needing a human to step in. We're talking 200 to 300 sequential tool calls.
Wait, 200 to 300 steps on its own? That's a massive jump in autonomy.
It really is. It implies a whole new level of robustness in problem solving.
Is there a concrete example? What did they show it doing?
The standout example was solving a PhD-level math problem. It took 23 steps, using reasoning interleaved with calling external tools, completely autonomously. It wasn't just guessing, it was using tools, checking its work, planning the next step. The community really sees this robustness as the true differentiator, the real moat.
But interestingly, the sources say the moat isn't just the model weights themselves, even though they're open source.
Exactly, that's the critical insight. The biggest challenge for competitors isn't replicating the 1T model, it's replicating the data that made it so capable.
So the training method is the secret sauce.
Precisely. The real IP, the thing they didn't open source, is the training methodology. They call it the industrial scale agentic skill factory. It's this whole pipeline using tons of tools, tool simulators, and the linchpin, something called the verifier economy.
Okay, verifier economy. Tell us more. Sounds sophisticated, like automated QA.
That's a great way to think about it. It uses other LLMs as automated judges, basically, verifiers. They check if the agent's solution attempt for a task was actually correct, based on specific criteria. It's like a massive automated rejection sampling system.
So it filters out bad solutions.
So really rejects the incorrect solution paths and only adds the verifiably correct ones, the successful trajectories, back into the training data. This constantly improves the model's reliability on complex multi-step tasks.
So the base model weights are free, open source. But the process to generate that incredibly high quality of verified agentic data, that's the proprietary moat.
You got it. They've shifted the value capture away from just the model architecture to the data generation pipeline itself. Very clever.
Okay, shifting gears to the economics, that price tag that went viral. Kimi K2 thinking supposedly cost only $4.6 million to train. That sounds suspiciously low.
Yeah, the reaction online was immediate skepticism, pretty much universally called a vanity metric.
A vanity metric, why?
Because the consensus is that $4.6 million, if true at all, is only for the final successful training run. It completely ignores the huge R&D costs, all the failed attempts, the infrastructure build-out, and maybe most importantly, the salaries and stock options for the specialized team that pulled this off.
So the real cost is much, much higher.
Oh, easily. Estimates put the true all-in cost in the several $100 million range. That's the reality check for anyone thinking AI is getting cheap at the high end. The R&D burn is immense.
Which feeds directly into that big debate. Is this whole 1T parameter race even necessary? Is it just, brute force scale for hype and stock prices, or does that scale unlock things smaller models just can't do?
Well, Kimi K2 thinking actually gives some ammo to the scale is necessary camp. It did definitively beat leading closed proprietary models on those really complex agentic tasks. That HLE benchmark, humanity's last exam, with tools.
Yeah.
Kimi got 44.9%. The competitor cited got 26.3%.
Wow, okay, so scale delivered a real capability leap there.
It seems so for that specific type of reasoning task. But importantly, the discussion also strongly validated the efficiency side. The counterexample everyone brought up was Minimax M2, much smaller. Only 200 billion total parameters and just 10 billion active during inference. Tiny compared to Kimi.
And how does it perform?
Remarkably well. It benchmarks very close to strong models like Claude Sonnet 4, but it runs way cheaper on much less hardware.
Okay, so that really crystallizes the market fracture, doesn't it? You've got the super expensive TAPL-intensive race for the absolute soda ceiling, like Kimi thinking, and then you have the pragmatic, cost-focused race for efficiency, like Minimax M2.
Exactly. But the conversation didn't stop at compute cost. The really forward-looking insight, the one that got people thinking, was about the next bottleneck.
Which is?
Energy scarcity. Not compute scarcity, but the sheer electricity required to power all this AI.
The power grid problem.
Right. The speculation is that the ultimate competition might actually become about securing energy resources. Someone pointed to China's huge investments in solar, potentially giving them a long-term advantage.
That's a sobering thought.
Yeah, the prediction was blunt. The current cycle of just buying more and more chips only stops when the electricity cost becomes truly unsustainable. It puts a massive premium on algorithmic efficiency, like Kimi's MLA, anything that reduces that enormous energy draw.
Fascinating. And speaking of strategic moves with global implications, let's talk about the license. Kimi K2 uses a modified MIT license. That sounded surprisingly generous for a state-of-the-art model.
It really is incredibly permissive. It's basically 99% standard MIT. The only modification is a simple attribution requirement you have to display Kimi K2.
And when does that kick in?
Only if your product using it makes over $20 million in monthly revenue or hits 100 million monthly active users.
Which, let's be honest, is a fantastic problem for any startup to have.
Absolutely champagne problem, as the comment said.
Yeah.
But here's the really crucial bit, the legal green light that got everyone excited.
Go on.
The license explicitly says it does not apply to the outputs of the model,
Ah!
meaning you can legally use Kimi K2 to generate synthetic data, or you could distill its knowledge into your own smaller, cheaper model without any licensing strings attached to that derived work.
Wow. That's effectively a massive subsidy for the entire AI startup ecosystem. They're giving away the SOTA capability to generate valuable data.
It's a brilliant strategic move, which connects to the bigger picture of China's approach here.
How so?
The thinking is that by open sourcing models this powerful, they establish a very high floor for their entire domestic tech industry.
A high floor
Yeah.
as opposed to a high ceiling.
Exactly. Instead of just one or two national champions having the best tech,
Yeah.
the high ceiling approach, arguably like the US with closed models, they give everyone a very strong baseline to start from.
So it prevents wasted effort on building mediocre models domestically.
Precisely. It forces the whole ecosystem to level up overnight. It prevents reckless investments in mediocre models, as one source put it.
Yeah.
And globally, it commoditizes that base model layer.
Which leaves founders everywhere with a really clear data-driven choice. We could almost call it the Kimi versus Minimax decision point based on their pricing.
That's a perfect way to frame it.
Okay, so on one hand, you've got Kimi K2 thinking,
Huh.
the heavyweight agent, 32 billion active parameters, higher cost, 2.49 per million output tokens.
Right. Best for those low-volume, high-complexity, high-value reasoning tasks where performance is paramount.
And on the other hand, Minimax M2, the efficiency champ, just 10 billion active parameters, much lower cost, 0.45 per million output tokens.
Yeah, over 5 times cheaper than Kimi K2. Ideal for high-volume, cost-sensitive stuff. Think chatbots, co-pilots, anything needing massive scale affordably.
Two very different value propositions built on open foundations.
Exactly. So if we pull all this together, what are the big investment takeaways? Let's maybe focus on the two most surprising or forward-looking theses for you, listeners.
Right.
First is what we could call Thesis 3, the Agentic data mode. The smart money shouldn't just be funding companies wrapping these base models. It should be funding companies building proprietary, high-quality data sets, using that Kimi K2 factory framework, that verifier economy idea. Because that specialized, verified data, that's the real long-term asset.
Got it. Data as the moat, enabled by the open model. What's the second big thesis?
That would be Thesis 4, the energy and infrastructure mode. This is the longer-term structural play. Investment has to start shifting seriously towards things like algorithmic efficiency, MLA is a perfect example, but also towards energy providers, maybe new hardware specifically designed to sip power, not guzzle it, because electricity will become the ultimate constraint.
Right. The physics eventually catches up.
It always does.
So wrapping up this deep dive, it's clear the Kimi K2 moment is way more profound than just hitting a big parameter number. We've seen incredible full-stack engineering, muon for stability, MLA for efficiency. We've seen the strategic genius of the Agentic skill factory and that verifier economy. And we've seen the global implications of China's high-floor open-source strategy.
Absolutely. It's a complex picture.
And the main takeaway for anyone building or investing in this space seems crystal clear. The market is splitting, a bifurcation. You have the closed, super capital-intensive, high-ceiling race at the very top, but you also have this burgeoning, open, cost-effective, high-floor race.
Yeah.
And it feels like that second race, the high-floor, efficiency-focused one with models like Kimi and Minimax, is where most of the practical, profitable startups are actually going to be built.
I think it's a very strong possibility. Cost and efficiency win in the real world most of the time.
Okay, but let's end on that really provocative thought that came up in the sources, tying back to energy scarcity. We're talking about AI needing so much power and energy becoming such a bottleneck globally that some U.S. tech figures are apparently starting to speculate, maybe half seriously for now. What happens if securing enough energy becomes so difficult here that major U.S. tech companies seriously consider moving core AI operations out of the U.S., maybe to places like the Middle East, purely for the energy resources?
Hmm.
It raises a fundamental, almost unsettling question about the long-term sustainability and, frankly, the geopolitical security of relying solely on this ever-scaling compute model right here at home. Something to think about.